Right, let's try that again. Good evening, everybody. Tonight I'm going to fly through the first section of the chapter. I assume that you all have read through it and is more or less familiar with what's going on there. Um, Alternating current um, in DC, direct current, the terminals is positive and negative, and in the circuit, the flow is also always from positive to negative, and the current flow is only in one direction. In an AC circuit, an AC stands for alternating current. The polarity changes from positive to negative continuously. Although the abbreviation AC stands for alternating current, it is also used to refer to voltages in phrases as an AC voltage or 15-volt AC. So if I tell you I need 15-volt DC, then you'll know that it will be 15-volt direct current. If I say we need 15-volt AC, that would mean that it would be alternating current. If we plot the voltages or current in an AC circuit against time, there are many possible shapes known as waveforms that they could take. For example, first one there is a triangular wave. Okay, let me just scroll down, then you can see as well. And then below that is a square wave. However, when we analyze a AC circuit, we normally think of the waveform as being a sine wave or sine signal. Now, the complete word is sinusoidal, but for the ease of talking, we refer to a sine wave, and we regularly use sine waves to test different things. And then sine wave is a mathematical concept, but it describes something that occurs frequently in nature. Mechanical vibrations, rotating bodies, and electrical circuits, among others, can be described with the same mathematical models. To understand a sine function, we start by looking at rotating bodies. Visualize, where is that thing? I'm going to scroll to, it's just, well, it's going to just fit. To visualize a point on a circumference of a rotating wheel. Now uh, think of only about the vertical displacement of a point from the center axis. The quantity marked as A, which is there in the figure below, if the wheel rotates at a constant speed, a sine function is produced by the value of A. To the right of the wheel is a graph. The horizontal axis represents the phase or angular displacement of the wheel from some arbitrary standing point starting at 0 degrees, and the amplitude above or below the zero line is transferred to the graph as well. The relationship between the angle and the radius of the circle R is the amplitude A, and it's given by this formula here. Now, we're not going to spend much time on that because we'll start to do calculations with it just now. So, what it basically means is as this thing rotates around, you will get your sine wave drawn over here, which you get the peak over there. And then if this was voltage, it would start to deteriorate. And over here, the voltage goes into the negative half and then completes the 360 degrees. So this is the 0 degree mark, 90 degree, 180, 270, and 360 degrees. Here they say it decreases after 90. That's what I said over there. After 90, it decreases. The amplitude at 120 degrees is the same as it was at 60 degrees. So 120 there and there, and you can see that line runs straight through. And then when it goes negative, the shape is the same, but it's inverted. Each rotation of the wheel represents one cycle of the waveform from an angle of 0 degree to an angle of 360 degrees. And the sine function is applied as that formula. You must get well acquainted with the 2 pi. You're going to use 2 pi, whatever behind it, a lot. And then pi, we work with a pi that's on the calculator. So we've got a couple of extra digits there. And then here is an explanation of the values, but it's not really relevant because we're not going to actually use this. The sine function does not consist of two semicycles, which is how it is sometimes incorrectly drawn. So a half cycle is that part. So that is not a sine wave. A sine wave is the complete one. Um, the reason why we deal mostly with sine functions, and then my mouse jumps by itself, in the circuit analysis is because the French mathematician Joseph Fourier at that time showed that any other periodic function could be decomposed into a number of sine functions of different frequencies. If we know how a circuit responds to a sine signal, we can easily calculate its response to any other signal using the technique known as Fourier's analysis. A sine signal represents a pure AC signal that contains only a single frequency known as the fundamental frequency. Any other signal includes both fundamental and harmonics, which are integral multiples of the fundamental frequency. Okay, so we know that a pure sine wave is known as the fundamental frequency, and it doesn't have harmonics. You will often hear the term sine wave, although most radio signals are indeed sine waves as they travel through space. We are more interested in the sine shaped signals in electric circuits. To avoid clumsy constructions like sinusoidal signal, we therefore use the term sine signal to describe the voltage and current shapes inside the electrical circuit. AC signal consists of many identical cycles, one after the other. The figure above, that's now that other one with the wheel thingy on the previous page. One complete cycle of a sine signal. And then above that is the triangle and the square one, which we've already looked at. We know what a square one looks like, and we know what a triangle looks like, and we know what a sine wave looks like. Usually, electrical waveforms like AC voltages and currents are positive for half the time and negative for the other half. When we want to refer just to the positive or the negative period, we speak of the positive half cycle or the negative half cycle. And that is something I get to do with very often with amplifiers, because I would look on the oscilloscope, feed a 1 kilohertz sine wave into the amplifier, and I see but the bottom half cycle is missing, and I know then there's a problem on the negative part of the power supply. Period and frequency. The period of a waveform is the time taken for one cycle, which is usually expressed in seconds, milliseconds, or microseconds. Just for those who don't know, that is a microsine. And like I said, with capacitors, you might sometimes end up with a U there, because the microsine, to get that out of the computer is sometimes a bit of a pain in the backside. Definition: the period of a waveform is the time taken for one complete cycle. So from 0 to 360 degrees, that's one cycle. A complete cycle can start at any point on the waveform and continues to the corresponding point on the next cycle. But for sake of or for ease, we start at 0 and end at 360, because it's just easier. 0 and ends at, well, 0 again, but it could also be 360. So one complete cycle. But it could start anywhere. That's basically what they're trying to say. A frequency. So if we get one cycle, if we get the second one, then we have a frequency. Frequency tells you it happens frequently. So hence the word frequency. Uh, the frequency of a waveform is the number of cycles per second. The unit of frequency, one cycle per second, is called hertz, in honor of the German physicist Heinrich Hertz, to the power of 5. I didn't know that. The dimensions of the unit hertz is the same as per second. And then they give us the definition again. The frequency of a waveform is the number of cycles per second. So they really want us to remember that. Since the period is the number of seconds per cycle and the frequency is the number of cycles per second, it follows that the period and the frequency of the waveform are reciprocals of each other. That is, time, t, equals 1 divided by frequency, and frequency equals 1 divided by time. And there they say where t is the period and f is the frequency in hertz. For example, and now that is where we pull our calculator closer. So we say 1 divided by 50. So it's 1 divided by 50 equals 20 milliseconds. Okay, we're happy with that. But we could also do it like this. 50. I didn't really need the bracket there, but I mean, seeing that it's there, it's a bonus. So that will give us the same answer. So that is 20 milliseconds. Now that is so the two cycles, the complete cycle takes 20 milliseconds before the next one starts. So 10 milliseconds in the positive half and 10 milliseconds in the negative half. And that is very slow. Wavelength and the speed of light. Electrical current and voltages move through wires at almost the speed of light, which is a very, and my mouse jumps, which is a very high but not infinite speed. Radio waves transmitted from an antenna also travel at the speed of light. The speed of light, which is usually represented by the symbol c in physics, is approximately 3 times 10 to the 8 milliseconds. And that is reasonably fast. That's very fast. Think about an AC waveform with a constant frequency moving through a very long wire at the speed of light. At the start of the one cycle, the start of the one cycle will occur at a particular point in time, and hence at the particular point along the wire. The start of the next cycle will occur a certain time later. This time difference being the period of the wave during which the wave, which, oh, this is a difficult travel the speed of light. Okay, the distance is known as the wavelength of the wave. Definition: the wavelength of a wave is the distance traveled in one cycle. Because the wavelength represents the distance the wave travels during a certain time, it is related to the period and frequency as shown. So, right now that is a lambda sign. So it comes from the Greek lowercase l and pronounced lambda. So lambda equals, or the wavelength equals, the speed of light divided by time. And lambda equals the speed of light divided by frequency. For example, one of the author's favorite radio stations is Cape Talk, which broadcasts on a frequency of 567 kilohertz. The corresponding wavelength can be calculated as follows. Calculate. Right, lambda, that's the wavelength, speed of light, frequency. So we say bracket 3 10 to the 8 divided by bracket 5, 6, 7, 10 to the 3, because that's kilohertz. Close the bracket and we say equal 529.1, close enough. So the wavelength is 529 meters. Calculator gone. This is the distance that the radio waves transmitted by Cape Talk will travel during one complete cycle. There is a shortcut that is quite useful for radio amateurs because we express most of our frequencies in megahertz, millions of cycles per second. So you can avoid having to deal with lots of zeros or with scientific notation by using this formula. And 300 is the magic number, and you're going to use it a lot. And if I say a lot, I mean really, really a lot. Because if you want to make yourself a HF antenna, you're going to do the calculation with that. So we have a frequency of 14.1 megahertz, and we must calculate the wavelength. And let's just get our calculator closer again. No, wrong button. Right button. Good. Right. So that would be 300 divided by 14.1 equals 21 meters. If you want to build yourself a end-fed half wave, you'll divide that by 2 because you want to use half the wavelength, and that's 10 meters. You get yourself, well, slightly longer than that, just to be safe, and then you build yourself a half wave antenna for that frequency. And of course, if the frequency change, the antenna must change. And somewhere we're going to read that the higher the frequency, the shorter the antenna. Oh, note that the higher the frequency, the shorter the wavelength, vice versa. There we go. So once again, now here's a type O. They that's supposed to be meter and not megahertz, and I see it's carried over exactly the same into the online system, but we will fix it in the very near future. So what they want us to do there is they want us to calculate the wavelength for, no, the frequency for 2 meters. So we're going to divide that by 2, and that gives us 150 megahertz. So that is indeed correct. And then there they say the frequency limits is 144 to 146, but we describe it as the 2 meter band. So we don't want to, let's say 145, 300 divided by 145. So we're not going to describe it as the 2.0689 meter band, because I apologize. That's my phone telling me that somebody sent me a message. Right, carrying on swiftly. Now, I'm going to just sum this up, because what it basically means here, we've got a cycle that starts and completes over there. But here we've got a cycle that has already started actually over here. So these two cycles are out of phase. And you can have many of them, one after the other, that has a phase difference, as they say over here. In this particular case, this one is 90 degrees out of phase, so the one leads the other one by 90 degrees. And that's just something we're going to work with, trailing and leading with capacitors, where the current through the capacitor leads the voltage, and vice versa. So, right, RMS voltage and current. Now, I'm very sure that you have encountered RMS before, because when I was a lighty, we wanted amplifiers and speakers, and when you brag about your amplifier, you tell him that it's got 50 watts, and then just for good measure, you add in RMS. Not that you knew what it was for, but you just had to say it because you heard everybody else saying it. Right. So, in short, basically, what RMS is the amount of power a AC circuit will produce if it were a DC circuit. So in RMS, we can actually apply DC circuit formulas because we work with RMS. And RMS is root mean square. En in Afrikaans is die wortel van die gemiddelde kwadraat. You try and explain that to an English guy. um, right, we're going to work with figures just now. So there they say would calculate equivalent to DC voltages. Root mean square. So that's correct. The RMS value of an AC voltage is the value of the DC voltage that would cause the same power dissipation in a resistance. But what is extremely important is this only applies to resistive loads like uh, heaters, uh, incandescent lamps. If you go to transformers and in DC, AC motors, uh, there's inductance, and that is a whole different animal, which we will get to. Right. Now, in order to calculate the RMS, you would use the peak, voltage peak, divided by the square root of 2. And that is 0.707. And that's also a number you can remember because you're going to use it regularly. Note that this formula only works with sine wave signals. The radio may be different for other, the ratio may be different for other waveforms. So, yeah, that's only for sine wave, but in our circumstances, we're going to mainly work with sine waves. So, whenever one gives a voltage, a value of an AC voltage, the value is assumed to be the RMS value unless specified otherwise. So if I tell you I need a transformer with a secondary voltage of 15 volt, it would be 15 volt RMS. Most multimeters measure the RMS value, and then you get some that says they measure the true RMS value, which you then pay a lot more for. But for all practical reasons, most um, multimeters are accurate enough unless you do very, very specific work. For example, the mains voltage in South Africa is 240 volt AC. This means RMS value. So in order to calculate the peak value, we'll call our calculator. No, wrong button again. Right, and we'll say that the peak value is there's a square 2 equals. Okay, so this is the one value, but if you do that to this, it becomes 0.707. So don't be alarmed if it looked like that. It's just a reciprocal. So it's still the uh, so if we say 1, let's do that, square 2 times 240 equals. Close enough, but let's just see if we can get closer. Let's say 1.41 like they used times 240 equals. Yes, I would have made it 340, but I guess it's close enough. Just want to do it again for good measure. Times 240. Yeah, that is a different answer. Okay. I just want to do it again. Aha, wait.
I think they're just not carrying significant digits. They just rounded before they multiplied. They rounded the square
Could
root to,
could
yeah.
could be.
So
I just want to make sure that it's not a my mistake. Yeah, it must be that because I mean I keep on getting that. Maybe they rounded it off and we used the whole. Could be. Um, right. Calculator gone. Okay, we've come across this. The RMS value of an AC current is the value of the DC current that will cause the same power dissipation in a resistance. Okay, this is the 0.707 that we worked with now, and you can calculate the peak, the RMS value by multiplying with 0.707, or you can get the peak value from the RMS value by dividing by 0.707, or times the RMS by 1.41, which is the reciprocal of this. The nice thing about RMS is that Ohm's law apply. We did say that. For example, if an element of a kettle runs at 240 volts RMS and has a resistance of 48 ohms, the current flowing through the element is. Right, so we call on a calculator again. 240. Okay. Obviously, Ohm's law, I equals V divided by R. So that is what we're going to do here. That's Ohm's equal 5, and that is indeed correct. Throw that thing away. Although we have noted that the 5 amp is an RMS value, it normally be not normally necessary to mention, well, that it's RMS. They did say that just now. If they give you a voltage AC, it's assumed that it's it is a RMS value. If it's a peak value, they will say that it's a peak value. Right, and then we can calculate the power, the wattage, V times I. 240 times 5 is 1.2 kilowatt. Um, that's very easy. I'm not going to do that with a calculator again. Okay, and once again, because we're working with RMS values, but if it's peak, if they say that you've got a AC voltage with a peak of, say for argument's sake, 300 volts, then you will have to first convert that to an RMS value, and then you can once again apply Ohm's law. Here they have all of that, but what I would suggest is just remember that 0.707 and that the RMS value is always lower than the peak value. And then you use that to divide or multiply to calculate whatever you need. Right, frequency ranges um, and terminology. I'm sure a lot of you have heard about HF, VHF, and UHF, but it actually starts LF, low frequency, and then medium frequency, and there's the ranges. They do ask, I think one of the questions in the exam, they do actually ask you what is the range of HF, for instance. Yeah, they could probably change and ask anything else. Um, but that's just how it, I mean, they were doing development and they got to a point and I said, oh, we're using high frequency now. And that was cutting edge. And then it got a little bit better. And they said very high frequency, ultra high frequency. But then they ran out of ideas. And I mean, tremendously high frequency. I don't know what they're going to call it next. But for us, majority operates VHF, UHF, and I think we can almost add HF, H, SHF also, because a lot of hams are now playing around with satellite, and that is in the region of 2.4 gig to about, I don't know, Johan will know exactly what frequencies are available, but I think it goes up very high. So, yeah. In summary, AC signals consist of many identical cycles, one after the other. Sine signals consist of a single frequency known as the fundamental. All other signals have additional frequencies, the harmonics. The period of a waveform is the time taken for one complete cycle. The frequency of a waveform is the number of cycles per second. The wavelength of a wave is the distance it travels in one cycle. The wavelength and the frequency of a wave are related by the formula. Now that F is the frequency in megahertz. Here they say frequency in megahertz. Lambda is the wavelength, that's that thingy, and then M is the wavelength in meters, sorry. Phase differences are expressed in degrees with 360 degrees in one complete cycle. AC voltages and currents are expressed as RMS values. The RMS value of an AC voltage or current is the value of a DC voltage or current that would cause the same power dissipation in a resistance. For sine signals, the RMS voltage can be calculated from the peak voltage using the formula, and there they use the 0.707 that I told you to remember. For radio purposes, the frequency of an AC current is divided into two ranges. The most important range are HF, VHF, and UHF. Right, then we get to the questions. Right, the frequency of an AC waveform is defined in the unit. Now, this is where you guys must jump up and shout out and say,
D.
Hertz.
that's correct, D, delta. The frequency of 5 hertz has a period of,
Say 200 milliseconds.
that's correct. But for the sake of the calculator, we will say T equals 1 divided by F, which is the frequency. So we'll take 1 divided by 5, and that is equal to 200 milliseconds. Or we can also say 5 we can just do that. That's the other option. The wavelength of a signal of 100 megahertz in free space is, now remember I told you 300 divided by 100 equals 3. We can also say 3 to the 8. Let's just do that. Otherwise, we're going to not have a nice answer. Divided by 100, 10 to the 6, and we get 3 once again. So there's two ways of skinning the cat. If you know both formulas, you can calculate and see, make sure that the other answer is correct. So that would be C. Everybody agree? A radio
Yes.
wave has a period of 20 milliseconds. Its wavelength in free space is. So there we're going to use lambda equals speed of light times time. So that would be 3 10 to the 8. Put that in a bracket. Times bracket 20 10 to the 3. No, that's a minus 3. Somehow I think this is going to give me uphill. So let's start with that again. Right, that looks better. And then we say equal. Okay, that is 6 million meters. So if we make it kilometers, it's going to be 6,000 kilometers. So that's going to be D. Everybody agree?
Yes.
Right, this one you guys must answer. Two sine signals are 180 degrees out of phase. When the one signal is at maximum positive value, the other one would be at
C.
Right, so 180 degrees out of phase. So if the one is maximum positive, the other one would be 180 degrees. That's 90 degrees out of phase. That's 180 degrees out of phase. So the one they say is at its maximum value. Maximum value is at 90 degrees. So 180 degrees would be here. So it will be at its most negative value. So that's going to be B. Anybody that disagree with me? When one signal is at its maximum positive value, the other would be maximum negative value. Is it good?
Yes.
Yes.
Okay. Okay, this one you guys must also answer because I've said that repeatedly. Which signal consists of only the fundamental frequency without any harmonics?
Sine.
Sine.
That's a B. Good. Right, next one. Which value represents the ratio of RMS to peak value? And that would be 0.707. Agree?
Yes.
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 RMS is that of the peak. Peak
Okay.
times that, yeah.
What value of an AC waveform representing the equivalent heating effect of a DC voltage known as, that's RMS value. We've also repeatedly said that the RMS value is what a DC circuit will produce into a resistance. Okay, the mains voltage in the USA is 115 volt RMS. So what would the peak voltage be? 115 divided by 0.707. 162, so I'll go for 163. There's also the other one that you can do is 115 times the square root of 2 equals 162, which will bring you back there. Or you could say 115 115 times 1 point brings you more or less to the same value again. Let's get rid of the calculator. The mains voltage in South Africa is 240 volts RMS. If this voltage is applied across a heating element with a resistance of 576 ohm, how much power will be dissipated? Okay, then we at P squared R, if I'm correct. So we call on our calculator and we say we know that the voltage is 240. So we say 240 square. Where's it gone? Wonder if I've got to use that. Probably, huh? divided by resistance 576 equals. So the answer there is Charlie, C, 100 watts. Everybody agree with me?
Yes.
Yes.
Okay, good. Okay. See if we move the car. I can't get this calculator out of the way enough so that I can. An electric geyser operates from 240 volt RMS AC. Main supply consumes 2.4 kilowatt or then 2,400 watts. What's the current? So it's 2,400 divided by 240. And that is 10 amp RMS. Well, we don't actually have to even do the math because I mean they're all 10. The only difference is that that's an RMS value, so the result would be RMS. Right, a hi-fi loudspeaker have a resistance of 8 ohm. When it is delivering 8 watt, what is the RMS voltage across the speaker? Right, so our formula would be P equals VRMS squared, or P equals V squared RMS, depends on how you want to say it, divided by R. So if we manipulate our formula, we say VRMS equals the square root of P times R. So we say the square root, let's the square done, we do that, and we say 8 times 8 equals 8. And that is B. Okay, now, but there's a long way that you can do this now. Let's do it the long way. So we say 8 times 8 equals, yeah, what's happening there? 8 times 8, 64, and we square that up. Then we get to 8. So it seems like it's B, 8 volt. Everybody agree?
Yes.
Yes.
Good. Is there any questions? Just don't tell me do everything from the beginning again. No, I will, but not tonight. It's just, you know what, you've got to practice these things. It's maths, and the more you do it, the better you get at it. And it's basically, in this circumstances, it's the same as DC circuits for, well, specifically resistive loads. Right now, next week, is it next week? Where are we now? Thursday. Next week, we're going to do capacitors. And Almira, unfortunately, has got other appointments. And he asked somebody to do his presentation. And I said, I will. So we're going to do capacitors on Tuesday. What? Sorry, I'm just scrolling through to see what it all entails. See. Right. Any other questions about the work that we have? Well, any other questions in general? Let me put it that way. Comments?